Dear students, a very warm welcome to MOOC's massive open online courses on SWAYAM in chemistry. I am Charu Maini from DAV Public School, Sector 49, Gurugram. In this session, I will be presenting the first module on general principles and processes of isolation of elements. After going through this module, you will be able to explain the terms minerals and ores, analyze various methods used for concentration and benefaction of ore, understand the processes used to obtain metal oxides from their respective ores, understand the principles of oxidation and reduction as applied to the extraction procedures. You must have studied in your history classes about the evolution of human civilization. On the basis of the material used for making tools and machines for helping the growth of the civilization, the era was named as Stone Age, Bronze Age, Iron Age, etc. Thus, the development of human civilization passed from the Stone Age to Bronze, then to Iron, and now to our modern developed society, a society that is dependent on metals and alloys for its very existence. Since the discovery of copper, the metallurgical knowledge of the ancient man developed over thousands of years to investigate and understand the nature and use of the available native metal. The prehistoric man basically used metals which were gold, silver, copper, lead and iron. Over the years, the metallurgical knowledge evolved from an art to a science. The advancements in the knowledge of metallurgical processes became synonymous with the development of civilization. As early as 9000 BC, the use of wrought native copper. In 2000 BC, Bronze Age in the Far East. 1500 BC, Iron Age, Near East, and in 1826, zinc extraction in France. A few elements like carbon, sulfur, gold and noble gases occur in free state, while others in combined forms in the earth's crust. The extraction and isolation of an element from its combined form involves various principles of chemistry. A particular element may occur in a variety of compounds. The processes of isolation of elements should be such that it is chemically feasible and commercially viable. Some general principles are common to all the extraction processes of metals. For obtaining a particular metal, first we look for the minerals. A mineral is a naturally occurring chemical substance in the earth's crust, obtainable by mining. Out of the many minerals in which a metal may be found, only few are viable to be used as a source of that of metal. Such minerals are known as ores. Thus, we say that all ores are minerals, but all minerals are not ores. Rarely an ore contains only the desired substance. It is usually contaminated with earthy or undesired materials known as gangue. The extraction and isolation of metals from ores involves the following major steps: concentration of the ore, isolation of the metal from its concentrated ore, and purification of the metal. The entire scientific and technological process used for isolation of the metal from its ore is known as metallurgy. In the present episode, we shall focus on the first and the important step of metallurgy, that is, concentration of ore. We would describe the various steps involved in the effective concentration of ore. Let's have a look at occurrence of metals as minerals in the earth's crust. Selection of ore forms a very crucial step in the metallurgy of a metal, as this decides on the economic viability of the process. The principal ores of some of the metals, as you can see in the table, are aluminium ores are bauxite, which is a hydrated alumina, and kaolinite, a form of clay which is aluminium hydroxide, and silica complex. Principal iron ore are hematite, magnetite, siderite. That of copper are copper pyrite, malachite, cuprite, and copper glans. For zinc, it is zinc blende, calamine, and zincite. For tin, it's cassiterite. There is one interesting observation as we look at the composition of their ores, that is, metals exist in the form of their carbonates, hydroxides, and sulfides in nature and not in the form of nitrates. The reason for this is that nitrates of various metals are soluble in water. Now that we know about ores of metals, let us understand the processes involved in metallurgy. The first one is removal of unwanted materials, example sand, clay, etc. This is known as concentration, dressing, or benefaction. Concentration of the ore is the first step in the metallurgy as unwanted impurities, that is gangue, is removed in the step. Before concentration, the ores are crushed, powdered, and graded to a reasonable size. It involves several steps, and selection of these steps depends upon the differences in physical or chemical properties of the compound of the metal present and that of the gangue. The type of the metal, the available facilities, and the environmental factors are also taken into consideration while selection of the method of concentration. Some of the important procedures are hand picking. This is the simplest method as we do in our daily routine of cleaning of pulses in the kitchen. The process may be compared with the cleaning of pulses to remove small stones before cooking. In cases where the sizes of impurity particles differ from the size of the ore particle, the impurities can be removed manually by picking with hand. Generally, rocky particles and other coarse earthy material are removed by this method. Next, hydraulic washing. The concentration process of an ore by hydraulic washing method now may be compared with washing of pulses to remove any dirt before cooking. The principle is difference in gravities of the ore and the gangue particles. It is therefore a type of gravity separation method. Let us understand the method. In one such process, an upward stream of running water is used to wash the powdered ore. The lighter gangue particles are washed away and the heavier ore are left behind. The method has been in use for concentration of ores of tin and lead, as these are heavy and settle to the bottom where the dirt, that is gangue, is washed off. Another simple method is magnetic separation. You all must have played with magnets and used them for simple separation of magnetic substances like iron fillings from other components of a heterogeneous mixture in your lower classes. This method uses the same technique for concentration of ore. The principle behind is the difference in magnetic properties of ore components. If either of the ore or the gangue, that is one of the two, is capable of being attracted by a magnetic field, then such separations are carried out. Let us understand the method. The ground ore is carried over a large conveyor belt which passes over a large electromagnetic roller. The magnetic component gets carried away with the roller, whereas the non-magnetic component drops first and makes a heap. The magnetic component being carried away with the conveyor belt forms a separate heap. This method has been in use for concentration of iron ores. Another interesting method of benefaction of ore is froth flotation method. Before explaining this process, let us recall the cleaning action of soap. A soap molecule is a long chain fatty acid. It has a hydrophobic tail and a hydrophilic head. In water, soap or detergent molecules have a unique orientation that keeps the hydrocarbon portion of the detergent molecule away from water, forming micelles. These micelles lead to the formation of froth, which pulls the dirt and cleans the linen. Before we learn about the scientific technique of froth flotation, let me tell you an interesting story of an innovative washerwoman who led to the method adopted for concentration of copper ore containing copper sulfide. This story will tell us that how having a scientific attitude of asking questions and seeking their answers is so very important in life, and this attitude leads to innovations. A washerwoman, while washing the overalls of miners, noticed that sand and similar dirt fell to the bottom of the wash tub, and the froth used to shine like gold. What was peculiar? The copper-bearing compounds that had come to the clothes from the mines were caught in the soap suds, and so they came to the top along with the froth. And when light fell on them, the froth, it had a shine like gold. One of her clients was a chemist, Mrs. Carrie Everson. The washerwoman told her experience to Mrs. Everson. The latter investigated the property and the quality of the shiny material coming to the top with soap froth. She thought that the idea could be used for separating copper compounds from rocky and earthy materials on large scale. This way, an invention happened. At that time, only those ores were used for extraction of copper, which contained large amounts of the metal. Invention of the froth flotation method made copper mining profitable even from the low-grade ores. Word production of copper soared and the metal became cheaper. The principle behind the froth flotation is difference in the wetting characteristics of ore and the gangue. The mineral particles are wetted by oils while the gangue particles by water. This method has been in use for removing gangue from sulfide ores. Let us understand the steps in the method. In this process, first a suspension of the powdered ore is made with water. Collectors and froth stabilizers are added to the suspension. The collectors enhance the non-wetting ability of the mineral particles in water. Examples of collectors are pine oils, fatty acids, xanthates, etc. The froth stabilizers, as the name suggests, stabilize the froth. Examples are cresols, aniline, etc. A rotating pedal agitates the mixture and draws air in it. As a result, froth formed by the collectors is light and thus carries the mineral particles along with it to the top. It is then easily removed from the top. In the fifth step, it is then dried for the recovery of the ore particles. Sometimes the ore obtained from the nature is a mixture of sulfide of two metals. For example, an ore containing zinc sulfide ZnS and lead sulfide PbS. In such cases, the two sulfide ores are separated by adjusting proportion of oil to water or by using depressants. For example, in case of the ore containing zinc sulfide and lead sulfide, the depressant used is sodium cyanide. It selectively prevents zinc sulfide to come to the top and stick to the froth, but allows lead sulfide to come with the froth. Sodium cyanide forms a coordination complex with zinc sulfide, thus depressing it. Let us understand as to how. Sodium cyanide NaCN acts as a depressant in preventing zinc sulfide ZnS forming froth. NaCN forms a layer of zinc complex sodium tetracyanozincate Na2ZnCN4, thereby preventing zinc sulfide to form froth. The processes discussed till now were basically physical methods of concentration of ore. For some ores, chemical process of leaching is used. In general, leaching means to separate soluble constituents of a mixture by passing a suitable liquid through it. In metallurgical processes, the concept of leaching is used to convert the metal ore into a soluble compound and then filter off the impurities as residue. Leaching is often used if the ore is soluble in some suitable solvent. The following examples illustrate the procedure. First of all, leaching of alumina from bauxite. The principal ore of aluminium, bauxite, usually contains silica, that is SiO2, iron oxides and titanium oxide TiO2 as impurities. Concentration is carried out in the following steps. The first step, digesting the powdered ore with a concentrated solution of sodium hydroxide at 473 to 523 kelvins and 35 to 36 bar pressure. This way, alumina is leached out as sodium aluminate, leaving the impurities behind. Silica too forms sodium silicate, but it is removed in subsequent steps. In the second step, the aluminate in the solution is neutralized by passing carbon dioxide gas and hydrated alumina is precipitated. At this stage, freshly prepared samples of hydrated alumina are added to the solution to induce precipitation. This process is called seeding. So, we may say that the solution is seeded with fresh sample of alumina. In the fourth step, the sodium silicate remains in the solution and hydrated alumina is filtered, dried and heated to give back pure alumina, that is Al2O3. Now, let us see the metallurgy of silver and gold by the process of leaching. In case of metallurgy of silver and gold, metal is recovered in the following steps. For the first step, the respective metal is converted to a soluble metal cyanide complex by treating with dilute solution of sodium cyanide or potassium cyanide in the presence of air for oxygen. This water soluble complex is easily leached out as soluble metal cyanide complex. Second step, the metal is obtained later from its soluble complex by replacement with zinc, which forms a more stable tetracyanozincate complex. Let us see now extraction of crude metal from concentrated ore. The method used for extraction of metal from concentrated ore depends upon the nature of the metal. Based on their reactivity, the metals have been grouped into the following three categories. Metals of low reactivity, which lie low in the activity series. Second, metals of medium reactivity, which lie in the middle of the activity series. And third, the metals of high reactivity. They are placed at the top of the activity series. Reducing the metal compound to metal has following steps. For the steps involved in extraction of metal from its ore, let's have a look at this table. Thus, for metals of medium or low reactivity, the concentrated ore must be converted into a form which is suitable for reduction. Usually, the ore is converted to oxide before reduction. Oxides are easier to reduce. Thus, isolation of metals from concentrated ore involves two major steps. First, conversion to oxide, and second, reduction of the oxide to metal. Conversion to oxide. Conversion of concentrated ore to oxide can be carried out by either calcination or roasting. Calcination involves the strong heating of concentrated ore in absence of air. On strong heating, the volatile impurities escape, leaving behind the metal oxide. Calcination is the process in which an ore is heated strongly in the absence of air To convert a carbonate ore into metal oxide, when calamine ore, let us example for zinc carbonate, is heated strongly in the absence of air, it decomposes to form zinc oxide and carbon dioxide. Calcination is also used to remove water from hydrated ores and to remove volatile impurities from the ore. Next is roasting. In roasting, the ore is heated in a regular supply of air in a furnace at a temperature below the melting point of metal. In this process, a sulfide ore is strongly heated in the presence of air to convert it into metal oxide and to remove the volatile impurities. For example, when zinc blende, that is zinc sulfide, is strongly heated in air, that is roasted, it forms zinc oxide and sulfur dioxide. Some other reactions involving sulfide ores can be seen here. The sulfide ores of copper are heated in reverberatory furnace. If the ore contains iron, it is mixed with silica before heating. Iron oxide forms iron silicate, that is slag, and copper is produced in the form of copper matte, which contains copper sulfide and iron sulfide. The sulfur dioxide produced is utilized for manufacture of sulfuric acid. The comparison between calcination and roasting can be seen in the table. Now let us see the reduction of oxide to metal. Reduction of the metal oxide usually involves heating it with some other substance acting as a reducing agent, which may be carbon or carbon monoxide. The reducing agent, example carbon, combines with oxygen of the metal oxide as shown in the reaction. Some metal oxides get reduced easily while others are very difficult to be reduced. In any case, heating is required and the concept is called as pyrometallurgy. The word pyro comes from heat. As you know, reduction may be understood as gain of electrons or electronation and loss of oxygen. To understand the variation in the temperature requirement for thermal reductions, pyrometallurgy, and to predict which element will suit as the reducing agent for a given metal oxide, Gibbs energy interpretations are made. You will study about prediction of a good reducing agent and the suitable temperature for reduction of metal oxide to metal in the next module of this chapter. Let us understand why are carbonate and sulfide ores generally converted into their oxides. This is because a metal can be obtained more easily from its oxide by reduction. So, carbonate and sulfide ores of metals are converted into their oxides. Another thing that we studied is why can carbon reduce copper oxide to copper but not calcium oxide to calcium? This is because carbon has more affinity for oxygen than copper but less affinity for oxygen than calcium. So, let us summarize what we studied today. Metals are required for a variety of purposes. For this, we need their extraction from the minerals in which they are present and from which their extraction is commercially feasible. These minerals from which their extraction is feasible are known as ores. Ores of the metals are associated with many impurities and the removal of these impurities to certain extent is achieved by concentration steps. The concentration of ore may be brought about by choosing a suitable process out of hydraulic washing, magnetic separation, froth flotation or leaching. The method of reducing the concentrated ore to metal depends upon whether the metal belongs to high, medium, low or extremely low reactivity. After this, the concentrated ore of medium or low reactivity is usually converted to metal oxide by either calcination or roasting. And we studied that in general the metal sulfides are roasted and metal carbonates or hydrates are calcined before reduction to metal. So, this was about this module. In the next module, we will study about the various reducing agents and the temperature required to reduce a metal oxide to metal. Till then, thank you.